So the second topic we would like to address in this course is digital communications. We are done with analog, and now it's time to look at digital communications. We're going to divide this topic into two parts. The first one would be analog to digital conversion, how to do sampling and signal reconstruction. So in fact, in this part, there is not really much of communication. It's just how to go from analog to digital. In the second part, we'll look at digital transmission, how to transmit a digital signal from one location to another, and how this is different from analog communication. Now, to address the issue of the advantage of being digital or why we go for digital communication, we advise you to visit our Introduction to Communication video at the beginning of the course, where we discussed why digital communication. So now we'll focus on the first part, analog to digital conversion, and specifically our lecture topic would be sampling and signal reconstruction with some applications. All right, so the outline or the objective of our class will go like this. We'll start with why. We'll start right away. Since we addressed the issue of why digital, I'll just go right away to analog to digital conversion. We have two main steps there, which is sampling and signal reconstruction. We'll cover sampling theorem, Nyquist sampling theorem. What is the spectrum of sampled signal? That's a very important topic. And then we'll look at how do we reconstruct the signal. We'll look at the interpolation function and the zero hold and first hold approximations. How to get the signal back. We'll also address some practical issues related to sampling and signal reconstruction. The diagram on the side shows you an analog signal being sampled. Sample is a process that's done on the time axis. And then we have also to go from analog to digital, this is called ADC or A to C, analog to digital conversion. A to D, sorry. So we can say ADC or A to D. Okay, both will mean the same thing. A to D, analog to digital, or analog to digital conversion. The process of going from digital to analog is called digital to analog conversion. So we have ADC and DAC. And if we do ADC and then DAC with proper filtering, we get back our analog signal. So usually in the transmission, we do digital transmission, and then finally we want usually to represent our signal in its original format. If it was originally digital, I would like to get it digital. If it was originally analog, I will just go and get my analog signal after filtering. Now notice that not all signals in life are analog. There are some digital signals like texting with SMS message. It starts by being digital itself. So let's start with how analog to digital conversion occurs. In the following diagram on the following slide, I'm summarizing the basic steps in analog to digital conversion. So we start with analog signal and would like to go into digital. We advise you to go back and visit. If you don't know the difference between continuous time versus discrete time, then you might visit our previous videos in the review of signal systems to find out what's the difference between continuous time and digital time signals, the difference between digital and analog signals. So we'll assume that we are starting by a source of a continuous time message signal. And the process I'm going to illustrate is the analog to digital conversion, and it's also called the pulse coded modulation. How do we modulate, how do we represent the information into pulses? Okay, recall that the word modulation here does not really mean changing frequency. It means adjusting or representing. Adjusting for the objective of representation. So this is our continuous time signal. Okay, the first thing to do is to filter the signal using a low pass filter. Why? Will not state why now, but this is a needed filter. It becomes clear when we come to the issue of aliasing. But for now, we start by filtering, then we do sampling. Sampling is an operation that's done on the x-axis and the time axis, where we sample the signal. We take samples on the time axis. Then we do quantization. Quantization operates on the y-axis. So we are going to quantize to the nearest level on the y-axis. I assume all the audience has been exposed or have been exposed to this. We're just reviewing. So low pass filtering, sampling, quantization. Then we do encoding. Encoding will turn the signal into what we call pulse coded modulation signal, which means the information now is modulated into pulses and usually represented by zeros and ones. We have the PSIM signal, and we'll take the signal to the channel. Now, the pulses that we transmit, as you see here, as it travels through the channel, it loses part of its energy. It gets dispersed and changes with time. Okay, so the channel is not ideal. So with digital, usually there is something called repeaters. Before I lose the signal completely, I'm going to repeat the signal, recover the signal. So if you like, we can even send, for example, positive pulse or negative pulse to represent 1 and 0. Before losing the signal, here we still can say whether it's positive or negative. But if we wait longer, we might lose this. So we use a repeater to repeat the signal exactly as it used to be. Now, as the signal goes through the channel, it gets distorted. And to use the repeaters, how many regenerative repeaters do we need? It depends on the distance between the channel, the transmitter, and the receiver. So we have regenerative repeaters spaced by a distance to make sure that we are not losing the signal. Just before we get the received signal, at the receiver side, we start by clearing the signal, regenerating the circuit, regenerating the signal back. And the first step we'll do the opposite of encoding. So we have the blue block, and we're doing the decoding. So if you notice the colors here, the encoder will be decoded by the block, which is the decoder. So what's the opposite of a quantizer or a sampler? Those two operations together will be reversed by one block, which we call the signal reconstruction. So we have a reconstruction filter, and hence I have colored this kind of partially red, partially green, to show you that this block will do the opposite of these two blocks. I want you to be able to reproduce this. We have signal. If you close your eyes and then start sketching the diagram down, we have a filter, sampler, quantizer, encoder, and then we have repeaters. At the receiver side, we have decoders and signal reconstruction, and finally we are at the destination. So this is the process where we do analog to digital conversion and also digital to analog conversion. We want the signal to get back to its original shape. Now, we're now focusing on only sampling. How do we sample the signal? In sampling, forget about quantization, encoding. We just want to know how many samples should we take and how do we sample. From our background, we have been exposed to Nyquist theorem and sampling. Okay, so assume that this is my signal. Okay, this is the original signal, as you can see here. Okay, it continues with the dotted lines. And I want to take samples. How many samples should we take? The spacing between these samples is called the sampling interval, TS. All right? And our job is to find how many samples are required to get the signal back. Because at the end, what we want to do, like we have this in this little puzzle, okay? Usually give this to the kids, where we want them to connect the dots and recover the sketch. So the question we ask, how many dots do we need? Okay, so it depends on the details of the image, and the more dots we have, it makes the design or the reconstruction of the original image clearer. We have been exposed to this, and we came up with Nyquist sampling theorem. So I'm just stating the theorem. It says a signal whose spectrum is band limited to bHz. So the bandwidth of the original message is bHz, okay? The meaning of band limited, the meaning of this statement, band limited, is restated here. It means that the spectrum, okay, the frequency representation of the signal equals to 0 for values of frequency greater than the limit, which is b. So band limited to b-hertz is equivalent in math to saying the frequency representation equal to 0 for frequencies greater than b or less than minus b. Nyquist says if your signal is band limited, we can reconstruct the signal exactly from the samples. Although we are taking just samples, these values, we can reconstruct the signal back exactly using uniform sampling, which means the spacing between the samples is the same. So we have uniform spacing at a rate r greater than 2b. So the number of samples required, sampling rate, is more than 2b. So if the bandwidth, if this is a voice signal with bandwidth 4 kilohertz, I need at least 8,000 samples. Or I need more than 8,000 samples because the theorem says it's not equal to, it should be greater than 2b. So the minimum limit is 2b, but we need to be above that. And that's in samples per second. And sometimes we just write hertz. Okay, now if the sampling rate is more than r greater than 2b, then you can tell that the spacing between the samples, time, is inversely related to the sampling frequency. So the sampling time must be less than 1 over 2b. Remember that time and frequency are reciprocals here. So TS or sampling time should be less than 1 over 2b. Okay, and this is why our mobile phone, when it samples our voice, it takes 8,000 samples per second, because our voice is band limited to, the intelligible voice, the amount of power that's important is up to 4 kilohertz. We'll call this minimum sampling frequency Nyquist rate. So if I say a signal is sampled at Nyquist rate, you know it's sampled at 2b, and the Nyquist interval would be 1 over 2b. So it's a fixed quantity. Now, if you look at the diagram here, you'll find that we have the sampled signal, which we call G bar. Our original signal was G. G bar refers to the sampled signal. Okay, like this is G bar as function of t. It's made of deltas, and these deltas are weighted by the magnitude of the original function. So we're saying here the nth impulse, these impulses located at t equal to nts, has the strength or amplitude of the original function. Okay, that's the value of gt at t and ts. For example, at ts I have this value, at 2ts I have this value, depending on the original function. Now, we have seen how the signal in time, the sampled signal in time looks. It's made of impulses, so it looks like this, right? Now, the question we have is, what is the spectrum of this sampled signal? Okay, so to represent this mathematically, we can say that the sampled signal, g of t, I'm going to use blue color here. So this signal, g of t, okay, the signal g of t is continuous in time with bandwidth b hertz. All right, so the signal g of t is continuous in time with bandwidth b hertz. The sampled signal, okay, the sampled signal is nothing but the multiplication of a train of impulses, rather, spaced by ts. So if it's spaced by t, we say delta subscript t. This subscript t represents the time interval between every impulse and the other. If the spacing is ts, we'll call it delta of t, delta subscript ts, to represent a train of impulses that is spaced by ts. So remember that delta of t is just one pulse, delta of ts is a train of pulses, a train of impulses. So in math, we can represent the train of impulses by a delayed and shifted deltas. They go from minus infinity to plus infinity. And we can say that the sampled signal G bar of t, okay, is going to be the multiplication between the function, the original function here, g of t, and the train of impulses. If you multiply them by each other, you get the sampled signal. Why I'm doing this? I am representing this in time because finally my objective is to go to frequency and see what's the spectrum of the sampled signal. If we continue, take the GT of inside. So what we have done is just taking GT inside, not much. And then we can apply the shifting property of the delta or the impulse and take the shift here. We get the following representation. This is how we represent the sampled signal. I will take this last equation to the next slide and we'll take it from there. All right. So let's say that this is a signal in time and this is the spectrum, assumingly we're just using a triangle to make things simple. The question is, what is the spectrum of the sampled signal? What would be the spectrum of these samples? Of course, remember that these dotted lines are just there to illustrate the idea, but we are just having impulses. The question is, what is this spectrum here? According to the math that we have seen before, okay, we can say that the sampled signal, which we have seen to be equal to the function multiplied by deltas, can be represented in this format. How? Remember that the train of deltas or impulses is a periodic function which can be represented by its Fourier series. So this is a Fourier series representation of the train of impulses. And we find that we have a constant 1 over Ts. The constant does not change with n. So we got outside, and this is called the exponential Fourier series or the complex exponential Fourier series. I will take these deltas and replace them with the equivalent here, and I got the following expression. Now recall from Fourier transform properties, what is the spectrum of this here? What's the impact of multiplying by complex exponential? According to the properties that we have seen before, that we have a scaling property here, and then we have shift in the frequency domain. Multiplying by complex exponential maps to shifting in the frequency domain. So the conclusion, this is a very important equation that we should remember by heart. Using ideal impulses, the spectrum of the sampled signal is the same as the spectrum of the original signal, but shifted to multiples of the sampling frequency. So if I take this signal and sample it with 1000 samples per second, I will get the same spectrum, another spectrum at 1000, 2000, minus 1000, as the summation goes from minus infinity to infinity. The other very important forgetting factor, it will be scaled by 1 over Ts. So we have here A, it's going to be A over Ts. Let me show you the diagram. So this is the spectrum of the original signal, and this is the spectrum of the sampled signal. The amplitude is scaled. Okay, what we have here is A, just to enlarge, A divided by Ts. Okay, and all of this is shifted at multiple frequency. If you use omega, it's going to be 2 omega s, or if you use frequency, it's going to be 2 fs. Okay, so if somebody asks now, how do we go from this signal to this signal? How do we reconstruct the signal? In time, we are asking, how do we connect these dots? How do we go like this? Or should we go like this? In time, it's not an easy question to answer. But if you look at the frequency and somebody says, how do we get this part of the spectrum from this repetition of images? The answer would be very simple. Okay? The answer is the use of low pass filter. So we have a filter here, okay, as we're going to see in the coming reconstruction slides. All right. So now the upper spectrum is the magnitude of the sampled signal. Okay, here the use of omega or f will not make a huge difference. So the magnitude of low pass filter, if you want to recover the signal with the original spectrum and the original amplitude, then the amplitude or the gain of this ideal filter should be Ts. If you use Ts, then the spectrum here will have an amplitude of just A. If the spectrum here has an amplitude of 1, then you get A over Ts. So it seems that signal reconstruction is a simple low pass filter, and we have to be careful now when we sample, and just to make sure that the samples do not overlap, because if these images overlap, then what happens is we cannot reconstruct the signal. So if you look at the value here, okay, in terms of frequency, this is equal to B. Let me use this different color. This is B, and this is Fs minus B. So we should say that Fs minus B should be greater than B, okay, so that these two do not overlap. This point is Fs minus B. It should be greater than this point, which is B. I'm using F. In that case, Fs would be greater than 2B. And with that, we have proven Nyquist theorem. We have proven that for the signal to be reconstructed correctly, the sampling frequency should be greater than twice the highest frequency. And if this is not the case, a problem is going to occur. Signal reconstruction. Now, we know that to reconstruct the signal, we need a low-pass filter. We would like now the opposite. We'd like to see things in time. How do we connect the dots or the impulses in time? So the interpolation, we mean by interpolation, is the process of reconstructing continuous time signal from its samples. We have samples, okay? And we'd like to know, how do we connect these samples together? What is the procedure? Should we go straight line? Should we go like this? Okay, this is the reconstruction process or the interpolation process. Okay, we know that ideally we need a low-pass filter with bandwidth of B, okay? And we can write mathematically in frequency domain this low-pass filter as this is the direct function, okay, or capital by function. The width of this filter should be 2B because we are considering the negative and the positive. And the scaling amplitude should be Ts if we want to get the same signal or the same magnitude as before. So let's go now work backwards. Let's go to the time. If you go to the time and use inverse Fourier transform, you'll find that the inverse Fourier transform will be a scaling factor by sync, which means that the impulse response should be sync, which means for every impulse we should have a sync. Now, this is how the sync look like. Okay, the simple sync would look like. Now, to get the signal correctly, according to our analysis, we need to replace every delta by a sync. Okay, we come here, another sync, a third sync, and so on, and then we add them all up to get the perfectly connected signal. This is equivalent to low-pass filtering. A special case, if we are doing at Nyquist rate, remember at Nyquist rate, Ts equals to 1 over 2b, which means 2b times Ts equal to 1. So we can replace this with just 1, and we simply can say that the impulse response or the interpolation function is just a sync function with the following coefficient. Now, observe that this interpolation function is going to pass by 0 by all other samples, which means they do not change other samples, but they give you the sample of interest, and they help you to find the interpolation values, and they don't affect the other samples because they cross 0 at multiples of the sample location. Now, the following diagram shows things in a better and clearer way. If you look at this diagram, basically these dots represent the samples. These dots represent the samples, and we're replacing the samples with sinks. Now you can see these sinks, okay, up and down. Those sinks now, if you add them up all, they will give you this solid connected line. Okay. All these sinks, if added together, they will give you perfect reconstruction. And this is how things look in time. It's not simple connection like this. It's a replacement of sink to every little sample. Now the output of the reconstruction system is, if you have many samples, it's basically convolution. Remember that if you have the impulse response and you want to get the output, and we have discrete input, so this is the convolution. Instead of integration, we have the summation. So this is the discrete convolution. Give me the samples, I substitute here, and I'll give you the connected function. So this expression, this equation is very important. We call it the reconstruction equation. You give me the samples, I substitute, and I get the reconstructed equation. A special case, of course, if we have been doing things at Nyquist rate, if you want things to look simpler, we can open this bracket, and at this specific scenario or case, we can write in a short way because 2b times ts is going to be 1. What remains is k times pi. Okay, so let's say that this is more general, and here is just for the case of Nyquist rate. Okay, so I would like you also to remember this equation, and we'll call it the interpolation formula, because the interpolation, given the function, given the samples, I would give you g of t, the connected signal. So please remember the equation here to be able to reconstruct the signal. Now let's look at an example. Find a signal g of t that's band limited to b hertz, and whose samples are. In this question, we are given samples, and we want to get the connected signal. Luckily, there is only one sample which is non-zero. All other samples are 0. So I will start with the, we're also told that this is sampled at Nyquist rate, so I can use the formula, the simple formula that we had earlier. I will substitute now. Luckily, in this summation, there is only one sample that's going to remain. All other samples are 0. If these were different numbers, I have to get you the expressions. For every single sample, we get a sink. So the answer would be sum of sinks. In our case, we have only one sink, and the only function that one sample give you one value, all other samples will give you 0, is the sink function. All right? That's a simple example because only one half sample. We have one sample. If we had 2, we expect 2 sinks, and so on. Usually, this is not done manually. I mean, we can do this using MATLAB or what have you. Okay. What we have seen was the perfect reconstruction. Some people could make things simpler. They could find the reconstructed signal by convolving the sampled signal with a simpler transfer function, not sink. They could use just a constant value, and this is called the zero hold value, because you get the value and you hold it. You get the sample and you hold. Another sample you hold. So your approximation in that case will be the red signal. It's like a staircase signal. It's not perfect. Alternatively, you can take it one step further, and you get a second order, or first order. This is a 0 order, and this is going to be a first order linear. And you replace every sample with a triangle. You can see the triangles, maybe the light colors. But when we add all these samples together, we get this connection, the red connection. Again, not perfect, but much better than the 0 hold order, or the 0 odd hold circuit. Okay, you can go to second order and so on. The infinite order, the best will be our sink filter, or what we call the infinite order, that if you replace every sample with sink and you add them all up, you get back your original signal, provided that you sampled above Nyquist rate. So in this slide, basically, we're showing you that this is the correct way of doing it. Because of simplicity, sometimes you want to implement first order or even 0 order reconstruction. Okay, in the following slide, I show you the two extremes. So on the left here, we see the 0 hold circuit, okay, where we have a constant. Okay, we replace every sample by a constant. In frequency domain, okay, this is the magnitude spectrum effect would be this is like using a filter with the following characteristics, as opposed to using ideal filter. So if your filter look like this, then you get a hold representation. On the other extreme, if your impulse response is sink, in frequency domain you have the rect, and then you get the perfect connection. Every sample now is replaced by sink, and we got the perfect connection. So this slide has nothing new. We're just showing you the two extreme. Here, the 0 hold, the simplest way. We're showing you in time, in frequency for the overall, and we have showing you the frequency, the time, and the overall. Take your time. You can pause the video and think about this to make sure that you grasp the idea. Okay, we're going to conclude with 2 slides about practical samples. Remember that we said in real life we cannot have sharp sampling, that there is no camera that can take images in 0 time. That's the lenses open and close in 0 time. We would love to have that, but in real life, to take the sample, this is like a transistor opening and then closing to get the reading. So we we would like to think, what's the impact of practical sampling? We don't have a train of impulses, ideal impulses. We have this kind of train. The only difference that's going to happen is that we'll get finite width practical pulses, not zero width. Because this is periodic, we can use a Fourier series representation. Remember here we had 1 over Ts. It was constant for all frequencies. But because of this practical sampling, we will get a constant that's changing with n, and it's usually decaying with n. So the spectrum will not get this Fourier series, but rather will get the following spectrum. So we'll have images shifted to the right and to the left, but the amplitude is getting scaled down. That's not a problem, provided that we have a guard band here. We sample above Nyquist rate, because this reduction in amplitude is not a big deal. We can always reconstruct the signal, provided we have enough guard band between them. For the last part, to avoid the need for ideal filters, because if these triangles were sharp, if we were sampling at just exactly above Nyquist rate, we will need very sharp filters to pick the signal out. If this triangle was here, the only way is to have ideal filters. To avoid the need for ideal filters and use gradual cutoff characteristics, a filter of this sort, okay, then we need to sample above Nyquist rate, not exactly. So if you want to retain 4 kilohertz, you might sample about at 10. If you have like 20 kilohertz, you can sample at 44 or 48 kilohertz. Okay, so we would like the filter to be gradual here, perfect, and would like it to be zero outside, which is not something easy to do. So if you study signals, and you'll find that it's impossible to force the response to zero for adjacent spectrum. And if you want to explore this more, you can study the Paley-Wiener criterion, but it's beyond our scope here. We just want to say that you have a problem here and you have a problem there, because if your filter is gradual, okay, your signal is going to be affected and the next image will be involved. So you better push this to the side by sampling at higher Nyquist rate. You get one triangle here, another triangle here, third triangle here. So your filter characteristics will be less important. Even if it goes close to zero, you would get still a very good response. So in the last two slides, we have seen the impact of practical sampling, not a big problem. For practical reconstruction, we need to sample above Nyquist rate. Okay, thank you for your attention.